Good afternoon, CS109. How are you guys doing today? What I like to hear. Okay, we have a wonderful class. We're going to do exciting things and learn important things. Actually, to give you a sense of how exciting a day it is, not only are we going to be learning one of the profound ideas that takes us from basic probability theory to being able to solve very interesting real-world problems, we are also going to get deep into one of the historical mysteries in the United States, which was the authorship of a particular set of important documents called the Federalist Papers. We're going to learn a little bit of probability, has an important theme to it, and we're going to be able to solve this cool problem by the end of today. So a lot to look forward to. But before we jump to that, we're going to do a little bit of review. And before we do any review, I do want to just make one quick announcement. The quick announcement is we have a midterm in CS109. It's not next Tuesday, it's the Tuesday after. So it's a long time from now still. We'll give you more details about it, but I just wanted to let people know that there's a lot of classes that have midterms on exactly our day. And after talking about it amongst the head TA team, we decided that the most reasonable thing to do was to let there be two offerings of the midterm. If you can make either of them, you choose which one you go to. You can either go to our normally scheduled midterm on the 1st at 7 p.m., or you can go on the 2nd, you can go to the 8 p.m. midterm. If you can't make either of these, you will have to let us know. So we imagine there'll be few people who can't make either time, but if that is you, then you should fill out this form. But we have just one small detail that we need your help with. If absolutely everyone comes to this midterm, we would need a slightly bigger room. So all we need to know is which one of these you believe you're going to go to, and we need to know that by next Wednesday, if that's okay. There's a little form on the Ed Discussion Forum. Please go fill that out. Just say which one you're going to. And if for some reason you can't make it to either, there's also a form there for letting us know. Does that sound pretty reasonable? Okay. Yay. Speaking about pretty reasonable, some of our review. Oh, we're in such a cool place in CS109. The cool place we're in CS109 is we have finished counting theory. We finished core probability, where we learned things like the law of total probability and conditional events. Then we learned about random variables, and on Monday's class we learned about the last major random variable in our set of random variables. And now that you've thought about random variables on their own, it's time for this beautiful next section in CS109 called probabilistic models. What an exciting moment. Now, the last random variable we learned about is worth doing a little bit of review on because it is pretty important. That normal distribution shows up in so many assumptions and so many problems so many times in the real world. So we learned about the normal distribution. The normal distribution was the probability distribution that had this oh-so-canonical curve. This curve is in fact the probability density function. And we also learned in class that often when we solve problems, we'll use this other thing called the CDF. The CDF answers the question, what's the probability that random variable is less than an input number? It's monotonic because as the input number grows, the probability that your random variable is less than it can only go up. So here's a plot of a classic CDF for a normal. We learned a bunch of formulas, but I want to just focus on one for now, possibly the most important formula for a normal distribution. If you have a normal distribution with those parameters, and you want to ask the question, what's the probability that my random variable is less than some input, you use this wonderful formula. You take your input, you subtract the mean, you divide by the standard deviation, and you put that through this very important function called the phi function. Phi function is a pre-calculated function, which is technically the CDF of a standard normal. Every computer has it pre-calculated. There's lots of places where you can find it printed out. And that's how you find that probably a normal random variable is less than a value. It's so important that I wanted to do a little bit more practice on it. And I thought instead of giving you guys an easy problem, I kind of want to show you guys a bit of a higher watermark for how hard a normal problem could be just using that one equation I have given you so far. So to start up today, we're going to go dive deep into really challenging you on your knowledge of normals. I'll write down that equation that you guys need to know. So if you have a random variable that's a normal, so x is a normal, and it has a mean and it has a variance, then the probability that x is less than some value is equal to phi of that value minus the mean divided by the square root of the variance, aka the standard deviation. Okay, you guys ready for it? Here's my problem, and I think it's actually quite interesting. It leads to a surprising result. And the result has to do with how many computers do you need if you're running a website and you want to guarantee a certain amount of probability that you will not be able to drop any requests. So the story starts on this thing called Singles Day. You guys have heard of Amazon, right? Has anyone here heard of Alibaba? Alibaba is like the Chinese equivalent, and their Prime Day equivalent is this thing called Singles Day on 11/11. That is their busiest day of the year. They will buy computers to host their website. And they want to buy a certain number of computers based on the busiest time of year. And they want to buy enough computers that they're pretty confident that they will not drop any requests, that even if there's more requests than they expected, they won't drop any. Does the story make sense? Okay, let's talk about the problems of the details. On that busiest minute of the busiest day, we're going to assume that the number of requests you get are going to come as a Gaussian. Gaussian might not be the true distribution, but people might just make that assumption. This is the assumption we're going in with. You're going to buy K servers. Every server can handle 10,000 requests. So it's basically you have to think about when you purchase your hardware, your hardware can handle a certain fixed number of requests. Then you'll get a true number of requests. And if the true number of requests is more than you can handle, you're going to drop. And we want to buy as many computers such that the probability that we don't drop anything is greater than 0.9999. So we want to be pretty sure. And just to start this problem altogether, probability of no drops is, let's say R is the number of R computers. We buy K computers. Sorry. And that allows us to serve R requests. And R is going to be very simply equal to 10,000 times K. The probability of no drop is the probability that the true number of requests that come in are less than the requests for the computers that we can handle. So this is the same as the probability of no drop. Or, yeah, probability of no drop. That's just to start us off. As I said, this is a little bit of a high water mark. We want to figure out this. We've got this equation. I want you guys to think about it. Definitely take 30 seconds to think about it on your own. Then I'm going to give you 2 minutes with the person next to you. So just think about it. Okay. Talk about it with the person next to you. How could you figure out how many requests you need to be able to support such that the probability of no drop is greater than 0.99999? How could you solve this problem? Really just using this one equation. Okay, talk about it with the person next to you. This is going to push your knowledge, and then we're going to solve it all together. Okay. This is a hard way to start a Wednesday, but I guess I'm getting this like full speed into probability pretty fast. Oh man, it's a little hard to get started, but you know, one way of thinking about this is here I draw the CDF. So this is the equation of the CDF, but here I'm going to actually draw what that would look like if you were to plot it. And somewhere out here you have, this is the mean. But as values of R increase, the CDF of the random variable R will go towards 1. If you say, well, what's the probability of getting less than 1 billion requests? Well, you know, the probability of that will tend towards 1 as R gets bigger and bigger. At some point, if this is on the x-axis R, the CDF gives you the probability of getting less than R requests. So on Singles Day, at that busiest minute, the probability that you get less than R requests. As R is really small, the probability that you get less than 2 requests is basically nothing. But eventually there will be a number such that the probability you get less than R requests will be equal to 0.9999. And the way I wrote this up, I actually took a moment and wrote it up as if it were a problem set question. And here's how I wrote it up. I said, the probability that R is less than R, that is how you define the CDF. And use the capital F to be CDF. Can you guys see that? Is that too small font? Folks in the back, can you see? Huh? Yeah. Okay. So the probability that the true requests that show up being less than some input R, That's what a CDF is. A CDF answers that question, and we use the capital F as our notation for the CDF. And we're going to try and find the R such that this is equal to 0.9999. We want to find the CDF input that leads to this particular probability. That's a little bit backwards from what we normally do. We're normally calculating probabilities, but now I'm trying to find what input leads to a particular probability. If I put in the equation for a normal CDF, it looks like this. It's the phi of whatever the input is minus the mean divided by the standard deviation. I know what the mean and I know what the standard deviation are. So, I put those two things into my equation. And now this is a little bit uncomfortable. Normally we don't have a variable on this side of the equation. Normally the thing we're solving for is on this side of the equation. But now we do. We have that R. And this is a bit of a cognitive leap. If you want to solve for that R, you know what you can do? You can start to invert this side. And the first step is you don't necessarily want phi of everything. You want to do the inverse phi of both sides. So phi is a function that can be inverted. You can ask, what input into the standard normal CDF would give you 0.99999? Phi is an invertible function, and there's this thing called the inverse phi. If you looked up what input to the normal CDF gives you 0.99999, the inverse phi function would tell you 3.71902. The inverse phi function, it's a famous thing. Like if you go to our course reader, you can even get an inverse phi calculator right there. Sorry, that's the phi calculator. Inverse phi calculator here. So you can put in 99999. It tells you the value that you could put into phi that would lead to 4 nines is in fact 3.7. And did I lose my work? Okay. So we can know inverse phi is 3.7, and now you just have one equation, one unknown, and if you solve for R, you get that R is equal to that little expression. And if you say the number of computers you need is that number divided by 10,000, the number of computers you need is 103.7. By 104, and the probability that you will drop a request is less than 0.00001, and the probability that you can handle all of them is greater than 0.9999. That's pretty tricky. A bunch of you probably thought wow, that's tricky. I felt a little bit comfortable about this idea of a CDF, but now you had me do this inverse phi. I guess I'm pushing you guys a little bit with this review concept, but I just want to show you kind of like a higher watermark of where you could go. Sounding good? Questions, clarifications? Yes?
So just to summarize, what we're finding with R here is the number of servers we want at max our machines to handle. And what we do in the second equation is then we know every machine has to have supporting 700 servers, and we're going to solve from there.
Yeah, so R is how many requests we need to be able to handle, and every machine can handle 10,000 requests.
And we're calculating that based on the maximum value distribution.
Yeah, so here we know if we want to not drop requests, we need to have enough computers to handle this number of requests. That's a really fancy number. I think if you did 10 to the 6th plus 3.7 times 10 to the 4th, it's just like 1,037,000. So we need enough machines to handle 1,037,000 requests. And then every machine can handle 10,000 requests. So we just divide that by 10,000. Okay. Yes?
Do we ever care whether it's smaller than something or smaller or equal to something?
Yeah, so, I said we want to be able to have a higher probability than 0.999. What if I said you have to buy enough computers that you have a lower probability than 0.999? You'd be like, I'm going to buy 0 computers. And then you have a way lower probability than 0.999. You've got a 0 probability. But the equals is an interesting one. So if this question had said, I kind of treated this question like it was an equals, like there was a less than sign, and then really quickly, I just switched to what number is going to make this equal to. And I solved for that. And then once I figured out this is how many requests I need to be able to handle, I need computers to handle more than this or more requests. I'd say exactly equal isn't so necessary here. You just need to be able to handle this number or more.
is technically treated the same as probability of big R less or equal?
Oh my God, that's such a good question. So the probability that big R is less than R, that is the same as the probability that big R is less than or equal to R. That is because R is continuous. And in continuous random variables, we think of the probability of R being precisely R as being 0. Though I guess number of requests, even though we use the Gaussian, will probably be discrete. But anyways, because for continuous random variables, this is true. For discrete random variables, this is not true. Yeah, Gaussian, continuous. Okay, you guys rock. Thanks for playing along on that very hard review problem. While it was probably a challenge, you'll appreciate it in like either on the first or the second, depending on which midterm you decide to go to. Okay, so that's the end of practice. I do have a little bit more review. The normal distribution also had this other beautiful equation. This beautiful equation is not the CDF. It doesn't give you the probability that your random variable is less than a number. It's the probability density. So it's the derivative of the CDF. And we find that to be very useful in cases that will show up later in this week. Okay, I do want to skip that. Here's a funny thing you're going to need to know. If you were in a normal probability class, I probably wouldn't teach you this, but you're in probability computer scientist class, and I think because of that, this is something that I would like to let you know about. You've seen logs before. If I have log of x, that's a particular function that takes in a number and returns me back another number. And log of x equals y is an equivalent way of saying e to the power of y equals x. So it's kind of the inverse of the natural exponent. You guys have seen this before. The reason I need to bring it up, though, is for two reasons. One, log has some beautiful identities. If you've ever worked with logs, it turns out if you have the log of anything multiplied or divided or to the power, then you get these very nice simplifications. So logs are nice to work with, but there's this really, really important property that if you have the log of a product, it's the sum of the logs. So if you have the log of the product of many, many, many things, it's going to be the sum of the logs of many, many things. And spoiler alert, this is critical if you want to be a computer scientist using probability. And the reason is, it turns out computers have problems representing very small numbers. If you start multiplying, if these are probabilities, and you start multiplying them together, you get underflow issues where your computer can't represent a number so small. Like there is an actual number there, but your computer just can't represent it in its standard representation. But computers do much better when you're adding logs of probabilities. You end up in spaces where the computers can actually represent those numbers. And so even though log probabilities wouldn't normally show up in an intro probability class, they should show up in intro probability for computer scientist class because computers will be much better at representing logs of probabilities than probabilities on their own. Anyways, this is like a little bit of just reminders. We'll bring this up later again when we need it. Oh, and then you guys, we're going to have some more good times with some counting today. Do you guys remember we were doing counting? Some people are like, no, but I'll learn it again before November 1st or Wednesday, November 2nd. Anyways, we did counting and we did things like, hey, if you have n distinct objects, so there is n factorial ways of ordering them. That will come up again today. Particularly, this one counting problem is going to come up again today. One of the things you could ask in counting is, if you have n distinct objects and you're putting them to R buckets, and particularly you want n1 to go into bucket 1, n2 to go into bucket 2, nr going to bucket R. We talked about in class how this is the same as number of permutations of the letters of, say, Mississippi, where you have like n1 M's and n1 2's and nr S's, whatever. And this is the number of letters in Mississippi. And you could sometimes write you the notation. I just want to remind you guys of that result before we jump into today's class. Anyways, we'll bring this all up again when we need it. Okay. End of review. So, thank you guys for following along for my review session. The next thing in CS109 that we want to learn is this beautiful topic called probabilistic models. When you go beyond single random variables and you start thinking about random variables being random together. It's such a beautiful topic. It will allow you to solve big problems with larger data sets. But even though this is where we're going to go, we're going to be starting as simply as possible so that you guys can build some fundamentals. Because when we go from one random variable to multiple random variables, thinking about them at the same time, we're going to want to do so very intentionally. So we're going to start in the discrete world. And I want some motivation, though. The world is filled with interesting probability problems. There's so many of them, and almost all of them involve more than one random variable. Some interesting problems just require one random variable, like maybe if you're thinking about that ride-sharing problem, that was just one random variable, but many things require many random variables. And one motivating example I'll give you is WebMD Health. This is an interesting website. You go to this website and you put in all your symptoms, and after you put in all your symptoms, it tells you the probability that you have different diseases. So you can say like, I have dizziness, and I have a one-sided headache, and I'm a 30-year-old male. And it's like, you probably have a migraine, but you could be having a stroke. And obviously, this is a big probability engine, and it's got a lot of random variables. In fact, it's going to have random variables for every possible symptom. It's going to have random variables for every disease, and it's going to be thinking about all these simultaneously. And in order to do that, it had to go from one random variable to many at the same time, which is where we're going in CS109. We're not going to start with WebMD. That would be really cool if we could make it. Instead, let's start with something a little bit more straightforward to think about. Our good friend, dice. Single random variables is like we're thinking about a dice problem, and you're just going to maybe roll the dice, let X be the outcome, and you can ask the probability of a particular assignment to the outcome. If your dice has different outcomes, you can ask, what's the probability that X equals 1? You can say, what's the probability that X equals 2, or probability X equals 3? And we would generalize it to this thing called the probability mass function. And ideally, somebody would come up with an equation, a function, a graph that could summarize any query you could have about your single random variable into one function. That sounds good? Do you guys want to see what it looks like when you have two random variables? Well, if you had two random variables, when we think about outcomes and events, the most common one, and the one that's most general, if you could answer this question, you would know everything about your two random variables, is the likelihood of assignments to one random variable at the same time as an assignment to the other random variable. So what we call the joint assignment. So X equals 1 and Y equals 6 is the joint assignment to X and Y. This is the full probabilistic claim, but you can remove the and just put a comma, and most people use that sort of notation. But if you could say, if I roll two dice, what's the probability that the first dice is a 1 and the second dice is a 6? That's just going to be 1 over 36. But more generally, if you had two random variables, the metaphorical equivalent of the probability mass function, that complete information function, is what we call the joint probability mass function. And the joint probability mass function is now going to take in two inputs. Some assignment to the first random variable, some assignment to the second random variable, and it should give you back a probability. And if somebody gives you this thing called a joint, they've told you everything you would ever need to know about your random variables. So maybe that's the first major key. When we get into probabilistic models, which means you have more random variables than one, the most useful information someone could ever give you is this thing called a joint. Now, the joint distribution for two dice isn't that exciting because no matter what assignment you have for X and what assignment you have for B, it's 1 over 36. Well, I guess assuming A is in the range 1 to 6 and B is in the range 1 to 6. So if you were to draw this, one way you could do it is you could make a three-dimensional graph. But a lot of times we'll put these into tables. So if we wanted to visualize this most important thing, this joint distribution, we might just draw out the table. And that table has all the values assigned to one random variable and all the values assigned to another random variable. And then every entry here is the joint probability that the first random variable takes on this value and the second random variable takes on this value. It's hilarious for dice because it's just filled with 1 over 36. You certainly didn't need to do this, but obviously we're going to be thinking about random variables that would have more interesting entries. Questions? Concerns? Okay, shall we take this up a level? I want to just have us think a little bit about this table and what properties it might have. First of all, you need to know what every single entry in this table means. So if I give you an entry over here, hey, typo. I think it used to point one down. This would be that the X is equal to 4 and Y is equal to 3 because it's in the Y equals 3 row. I put these typos in just to make sure everyone's paying attention. But that's the most important thing to know first. What does one cell mean? Okay. Now that's kind of a boring random variable. One of the reasons a boring joint probability table. And one of the reasons it's boring is because every entry is the same. So I thought I would make it a little bit more exciting. This is real data that somebody collected a while ago in CS109, not me, but now we have it. A slightly more interesting combination of two different random variables. One random variable was what year somebody was in CS109. So freshman, sophomore, junior, senior, and all grad students, we unfortunately get lumped together like nobody even cares about the nuances of our personalities. And then we have the other random variable of their single interrelationship, or it's complicated. And at least this can be like slightly more exciting than dice to think about. This is a joint table. So again, you should be able to think about what one cells here means. Like if I say 0.1 here, is that telling me that there's a 10% chance that somebody's a junior? No. It's telling me that there's a 10% chance that somebody's both a junior and also in a relationship. And this is the complete information that you'd want to know if you wanted to think about a model that involved these two random variables, this thing called the joint. Okay, and that's your major key, joint distributions, complete information. You can actually answer any probabilistic question you want to about the combination of these two random variables if somebody gives you a joint. Conditional question, you can answer it. You want to just think about one random variable at a time? You can answer it. If somebody gives you a joint, you have all the information you need to answer any question. What a wonderful thing the joint is. Couple small notes. For intuition, my claim is that let's say X is dating status and Y is year. If you loop over all values of dating status and you loop over all values of years, and for every single iteration of that double for loop, you look up the probability of a current year and a current relationship status. If you add up all those numbers, my claim is that it must sum to 1 if it's a proper joint distribution. One way to think about that is any of these cells is mutually exclusive. It's not possibly both a senior and a 5+. You can't be both of those at the same time, even if you're coterming. You're in one of these. And so each of these categories is mutually exclusive. So you should be able to think about, if you want to think about either this or that, it should be just sum. And if you think about this or 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 this, it should be that sum. And because they're all mutually exclusive and they cover all possible outcomes, my claim is that if you summed up this whole table, it should sum to 1. Yes, question?
Is the PMF for the two variables always represented as a table, or are there other ways to represent it?
That's such a good question. So this joint probability mass function, if you have two variables, do you always represent it as a table? That's pretty common, but not always. And there's lots of other representations which we'll get into. Table is just going to be the first one that we can visualize the easiest. Yes?
I don't understand why, like, each of the rows themselves don't add up to 1.
Well, that's such a good question. Why don't the rows add up to 1? If you add up this entire row, it actually gives you something very interesting and very semantic. I'm not sure if it's apparent to somebody, but what happens if you add senior and single, or senior and relationship, or senior and complicated? Because they're mutually exclusive. This adding up is getting the or. So this or this or this, what's that describing? Yeah, you guys are getting, yeah, it would be describing the probability of senior. And is there one probability that somebody's a senior? No, yeah, not everyone's a senior, so that's why it doesn't add up to 1. But you're a little ahead of me because that's one of the things I did want to talk about in a second. Okay, you know, this never comes up, but I just want to point out, if somebody gave you a whole table but they hid one number, I don't know why they would do that. You're like, why are you so cruel to me? But they're like, I'm just testing your knowledge of this one fact. You know, of course, this would be whichever number leads to sum of 1. Okay, that's not that important now. Okay, though this question is interesting and is so related to the question you just had. I claim that you can answer any probability question, so I'm going to just start showing you that. The first one is, can you figure out the probability that someone is in a relationship in CS109? So that's just a question. I don't care about what year they are, I just care about whether or not they're in a relationship. Could you figure out that question from this table? Think about, why don't you talk about the person next to you, see if you can come up with a question. I'm just going to give you guys about 30 seconds to talk about it. Okay, because we had such a wonderful question a second ago, and you guys thought this through, hopefully this isn't so bad. First of all, semantically, if you want to know somebody's a relationship, You don't care if they're a freshman. It's like this or this or this or this or this, and because each cell is mutually exclusive, you're just going to be adding up these 5 cells. So it's this plus this plus this plus this plus this. If you want to be really fancy, you would write it like this. You would say, I'm going to sum, and this is saying over every year, I'm going to add up the probability where x is equal to in a relationship and y takes on each of those values in the iterator of your loop. If you add it up, this is a fancy way of saying just like add up these 5 values. And if you added up these 5 values, you would get a number which is the probability that somebody's in a relationship. And we can eyeball it. It's like 20, almost 30. Wait, let's say this is 30, 38, let's say 45. So there's like a 45% chance that somebody is in a relationship. You can do this for lots of things. You can say probably somebody's single. You can say probably somebody's a freshman. If you want to know somebody's probably is a freshman, you just kind of sum out the other way. If you want to know somebody's probably is a freshman, you sum this direction. And that would give you the probability of freshman. If you want to know somebody's a sophomore, same thing. There's a fancy name for this. This thing is called the marginal. And marginalization is like somebody's given you a probabilistic model which has many random variables, and you want to extract just one random variable out of it. Well, you marginalize out the other. Do you guys have a guess for why they call this the marginal? This is not that you should know, but it's just maybe somebody's like, I have a cute idea. Anyone feeling cute? Yeah.
Maybe it's something like the labels or the table like in the margin.
Yeah, they used to like do this stuff by hand back in the day before computers, and they would actually just write it in the margins. So you'd be like 0.02 plus 0.08, that's 0.1, plus 0.13, that's 0.23, and they would just write it in the margin over here. And so that's where it gets the name marginal. And you'd write each of your answers in this margin and in this margin. Anyways, fun fact, not that important, won't be on your midterm, which could be on Tuesday or Wednesday, depending on your choice. Okay. Anyways, welcome to marginal. We can get really formal about it. And I used to teach people by just showing people this equation, be like, it's the marginal. But I think by now you've seen it on this real world example. I think it's a little bit intuitive. If you have a joint table and somebody wants you to just get one random variable on its own, you just loop over all assignments to the other random variable. And you say, OK, you wanted probably that x is equal to a. Let's loop over all the values of y, and you get x equals a and y equals each of those values in the iterator. Kind of complicated equation for a pretty straightforward idea that you guys already find intuitive. And anyways, that's what the marginal is formally. I did want to make a connection to something we learned earlier. Earlier in class, we learned about the law of total probability, and there was this general form of the law of total probability that some people found scary. And the general form of the law of total probability says, if you want to look up the probability of some event, but there's some background event where that background event has different values and each of those values are mutually exclusive and they span the entire space, then you can extract just this probability by thinking about the sum of your event and this background event. Your event and this background event, your event and this background event, your event and this background event. It's the law of total probability that is a theoretical justification for why marginalization exists. In fact, they're the same thing, just expressed in 2 different ways. So if you found law of total probability confusing, but you found marginalization easy, you can use that as intuition and the other way around. If you find law of total probability easy, that explains to you why marginalization works. So just a connection that you might want to go deeper into when studying. We've already talked about it, why it's called the marginal. So these joint probability tables, somebody asked, is this the only way of representing probabilistic models? And the answer is no. It is a very common way because it's very complete and very easy to interpret. But there's this key problem. They can get so big. Let's give you an example. In our previous models, we had 2 random variables. But we're getting into the world where we want to think about lots of stuff. Like that WebMD had way more than 2 random variables. So what if we bumped it up to 3 random variables? So here I'm going to have a joint distribution between 3 random variables. Disease, and disease has 2 values, either 0, you don't have disease, or 1, you do. S is for smell, and smell can take on 2 values. You either don't have smell or you do have smell. And F is going to be your fever status, which is you can have no fever, low fever, or high. So we have a joint distribution over a disease and 2 possible symptoms. The complete information, if somebody was going to give you all the information you need to answer any probability question, is the joint. And in this case, that means they have to give you one number for every assignment to each of the random variables. So d equals 0 and s equals 0 and f equals num. There's one number. D equals 1 and s equals 0 and f equals num. There's one number. So you need one number for every possible combination. Now this isn't too bad. You've got 1, 2, 3, 4, 5, 6. You have 12 different numbers. A computer can easily represent 12. Somebody who's a scientist may be able to give you those 12 numbers. This all seems pretty reasonable. But where does 12 come from? 12 comes from, well, there's 3 assignments to f times 2 assignments to s times 2 assignments to d. So 3 times 2 times 2 gives you 12. So even though 12 is not scary, that multiplication is. Fun fact, if you want to marginalize and just figure out what's the probability that somebody has a disease, you could do a loop, but this time not just over one variable, but over all assignments to those 2 variables that are not disease. So you loop over all values of fever, loop over all values of whether or not people can sell, and say, what's the probability they have the disease, and each of my values that I'm currently looping over. If you add those all up, you get the marginal. It works for more than 2 random variables. Okay, so great though. We've got this. We can start to do some baby little WebMD. How cute. But we're like, no, our WebMD is going to have 10 random variables. We'll have like 4 different diseases and 6 different symptoms. Is going to be fantastic. And maybe each of those random variables can all take on 5 values. So how many unique assignments are there to the and of every single random variable simultaneously? How many cells would there be in a joint probability table? And a joint probability table should give you one probability for every assignment combination to all your random variables. So what do we have? Ooh, a nice little counting problem. Yay. Okay, I'll give you guys a second to think about it. If you had one random variable with 5 values, you'd need 5 probabilities. If you had 2 random variables and each could take on 5 values, you would have a grid that's 5 by 5. That's 5 squared. 3 random variables, multiply that puppy by 5. Because you need a grid for every assignment to the 3rd random variable. 4 random variables, uh-oh. What happens if you have 10 random variables? Tiers, all tiers. Just short-circuiting your keyboard on your laptop from all the tiers that have come down, because 5 to the 10th is an unreasonably large number. Now, maybe 5 to the 10th can be stored in a computer, but imagine the poor scientist who has to think about the probability for every single 5 to the 10th assignment. That's a bit of a problem. And this motivates why we need models. Like this 5 to the 10th combination might be the perfect way to represent any assignment to all your random variables, but we're going to have to make some simplifying assumptions, both so that we can estimate probabilities more effectively and also so that we can represent them into computers. Because even though 5 to the 10th could go into computers, what if you had 100 random variables? That's pretty reasonable, and 5 to the 100 becomes a real problem. So joint tables, they're your be-all, end-all. They tell you everything you need to know, but they have this numerical issue in that if you have lots of random variables, they're exponentially large. Okay, welcome to the world of probabilistic models. So sometimes the structure of a variable suggests a more efficient representation than using a joint probability table. And we're about to start exploring those, because if we want to do cool problems, we need to learn more efficient representations of the joint. At the end of the day, we still want to represent the joint. We still want to have that be-all, end-all. We just want more efficient ways than using this table. Does that sound good? Okay. I'm going to start with a problem where there's a lot of structure. And there's so much structure, we could represent a joint using something way more efficient than a table. Okay, here's my thing for you. I'm going to not flip 100 coins, but I'm now going to roll 100 dice. And you're like, whoa, we never did that. And the binomial would flip 100 coins, but we never rolled 100 dice. One of the reasons is because when you roll 100 dice, some weirdness happens. You don't just have number of heads as a random variable. You instead could have 6 random variables as your outcome. Number of 1s, number of 2s, number of 3s, number of 4s, number of 5s, number of 6s. Do you guys see how if I roll 100 dice, that there's actually 6 random variables that come out of it? If I flip 100 coins and I say how many heads, just one random variable. But dice have 6 outcomes, not 2. So there are 6 random variables. Someone who's really clever might be like, wait a second. If you tell me the assignment to 5 random variables, I can know the 6th one. So maybe there's a way of getting rid of 1 random variable. We're not going to go there right now. But I want you guys to just appreciate that if you roll 100 dice, you're now in the world of a probabilistic model. You don't just have 1 random variable as an outcome, you have 6. Just checking, if we wanted to use a probabilistic joint table, how big would that be? So you have 6 random variables, and what are the values that this one can take on? This one says, how many 5s did you roll in 100 dice? Can you get a 0? Yeah, maybe not that likely, but you could get a 0. Totally valid assignment. Could you get 100? Yeah, like 1 in a billion times you roll 100 dice and they're just all 5s, and you're like, what? So the possible assignments to this random variable, there's 100. And there's possible assignments to this random variable, 100. If you were to write this all into a table, instead of having 5 to the power of 10, what do you have here? If there is just 1 random variable with 100 assignments, your table would have 100 entries. If there was just 2, you would have 100 squared. But since there's 6, if you tried to do this the naive way, and you just said, I'm going to make a whole big joint table, that joint table would be just a bit too large. So you guys buy with me that this should be something we should be able to reason about? For a joint probabilistic model, the joint probabilistic mass function is what we really want to know, but this is too big. Okay. We are now going to learn our first probabilistic model that is more efficient than a joint table. But first, there's a question.
Yes, on slightly disease, smelling fever. I was wondering, when you have this table, they're supposed to sum up to 1, right?
They should.
So I was trying to sum these 0 individually these 0 doesn't sum up to 1.
That's right, it shouldn't.
It shouldn't.
So so what you're saying, it's absolutely okay to have like probability, during distributions that are split sometimes.
Yeah, and these are split by 1 random variable. Like if you say these are all the ones where d equals 1, if you add these up, you actually get the probability that d equals 1. And if you add these up, you'll get the probability that d equals 0. And the reason I had to split it was because with 3 random variables, it should actually be a 3-dimensional table. And I can't draw a 3-dimensional table on a 2-dimensional screen, so that's why I split it. Yeah, very, very good question. I bet a lot of people were thinking about that. And if I get to 4 random variables, oh my God, is that a problem? I have to get into this like weird splitting up of my tables. But yes, if we were super advanced, this would be like a cube of some sort with the 12 entries. Okay. So we're going to learn for the dice a more efficient representation. And I promise you this will go way more interesting than dice. Just like a binomial distribution became much more interesting than just coin flips, this is going to tell us who wrote the Federalist Papers. And on that cliffhanger, why don't you guys take your pedagogical pause, come back in 2 minutes, and we'll continue this conversation about monomial random variables. Okay. Let's gently come back because a couple people went to the bathroom. Just before we jump into things, can I ask you guys a question? Did any questions come up during the pedagogical pause? Do you guys think for 2 minutes you're like, wait, I really want to know something? Yes?
What does the 3-dimensional table have? Like maybe a cube?
Oh my God. Let's say there's like 3 options in one variable, 3 options in a second variable. Oh God, I'm going to draw my cube this way. Oh, now you find out how bad I am at drawing cubes. This is very embarrassing. What is this supposed to look like? It should also go like 3 units out this way, where you can choose your like x, your y, and maybe your z. Though realistically, because I'm so bad at drawing cubes, instead of doing this, I would say this is z equals 0. And then I draw z equals 1, and I draw my 3 choices for x and y and z, and then I draw z equals 2. And then you can imagine these 3 grids would be stacked on top of each other to make a cube. So this is like cube level 0, cube level 1, cube level 2. For anybody who's played 3-dimensional tic-tac-toe, now it's finally coming into utility. Okay, good question. Any other questions? Okay. So Today we're going to think about a beautiful probabilistic model called a thing called a multinomial. And it's like the big sister of the binomial. The binomial asks, if I run n independent coin flip experiments, what's the probability of getting k successes? But implicitly, it always assumes that means you get n minus k failures. And so a coin flip is interesting. It's just got two outcomes, a head or a tail. So like, if that's a binary outcome, and this is the probability of getting a certain number of successes, your probability of getting a certain number of failures would just be 1 minus this. It gets its name from this binomial coefficient. And we thought about this probability very deeply when we were deriving it. We're now going to be learning about the big sister version of this called the multinomial. And the multinomial doesn't think about coin flips that have two outcomes. It thinks about things like rolling dice, which could have 6 outcomes. But you guys remember when we did the coin flips? We didn't always set p to be 1/2. The metaphor was much more interesting when we let p be a parameter of the binomial. Then we could answer more interesting questions. The multinomial is going to use the many dice rolls as its metaphor, but just like in the binomial, I'm going to allow there to be different probabilities of all of the different outcomes. So the multinomial, the big sister of the binomial, instead of thinking about coin flips with 2 outcomes, it thinks about things like dice rolls with m outcomes. If you gave me a binomial, you'd tell me the probability of a heads. If you have m outcomes and the dice roll at 6, you have to tell me the probability of each outcome. Well, in this case, it's easy. The probability of a 1 is 1/6. The probability of 2, so probability of outcome 2 would be 1/6. Probability of outcome 3 is 1/6. They're all 1/6 for a dice roll. But to make this an interesting metaphor, we're going to allow for the creator of our multinomial to tell us the probability of every outcome on a single dice roll. It must be the case that if you add up all the outcome probabilities, it sums to 1. When I roll a dice, I'm going to get something. So if you take the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4, 5, 6, if you add those all together, of course that comes to 1. So in particular, it describes a joint probability mass function where you have a random variable for outcome 1, a random variable for the number of outcomes of outcome 2, and a random variable for the number of outcomes of outcome m. M is 6 for a dice. C is going to say that, we saw this many of this outcome, this many of this outcome, and this many of that outcome. If you sum up all the CIs, it must be equal to n. What was n again? It's our number of dice rolls. In a binomial, it used to be our number of coin flips. Now it's our number of dice rolls. So if you sum up all the CIs, so you had like 2 1s, 2 2s, if you add up all the numbers of different outcomes, it should come out to how many dice you rolled. And of course, as we said before, if you sum up the probability for 1 dice of each of the outcomes, it should come to 1. If you had this particular probabilistic model, you would not need to have a joint table with 100 to the power of 6 outcomes. Instead, you can represent all of that joint probability in a single equation. You just need this one equation. You don't need that massive table. And this single equation looks a lot like a binomial probability mass function. It says, what's the chance of outcome 1? And how many times did you see that? What's the chance of outcome 2? And how many times did you see outcome 2? What's the chance of outcome m? And how many times did you see outcome n? Multiply those all together is not sufficient because you have to think about how many ways you could order all of these outcomes, these n outcomes, C1 of which are of outcome type 1, C2 of which are of outcome type 2, and Cm of which are outcome type m. Let's try a concrete example. So I have here 7 dice. So I'm going to roll my 7 dice. You guys ready? Rolling 7 dice. Oh my God, that's exactly the same as what's on the slides. I can't believe it. If I count, I got exactly 1 1, exactly 1 2, 0 3s, 2 4s, 0 5s, and look, 1 2 3 6s. Don't check, please. The multinomial doesn't seem that helpful at the moment, but just to be precise what it's answering, it's saying, what's the chance of this exact set of outcomes? And you're like, how is that different from the chance of getting like 1 of each and maybe 2 6s? And it turns out you get different probabilities for different assignments of different numbers of outcomes. Wouldn't you know? And the multinomial tells you, okay, there's 6 random variables being random together. It's a joint. And the probability that this random variable equals 1, while this random variable equals 2, while this random variable equals 0, while this random variable equals 2, while this random variable equals 0, and while this random variable equals 3, we can think about that jointly using just a single equation. The single equation says, okay, what's the probability of a 1? I saw that once. What's the probability of 2? I saw that once. What's the probability of 3? I saw that 0 times. What's the probability of 4? I saw that twice. What's the probability of 5? I saw that 0 times. And what's the probability of 6? I saw that 3 times. Now, dice aren't interesting in that the probabilities are the same here. So that was going to be 1/6 to the power of 7 no matter what you had, because I rolled 7 dice. But this term will be different, which says how many different orderings can you have of 1, 1, 1, 2, 0, 3s, 2, 4s, 0, 5s, and 3, 6s. So it will change. Dice do have different outcomes depending on different assignments you put here. Okay, pause here, questions. Is it making sense? If you roll n dice, you now have a way to talk about the probability of the number of outcomes of each outcome type. Dice are harder to talk about because there's 6 different outcomes, not just 2 like a coin. Yes?
I'm confused about what the first term is representing. Is that 7, 2, 6?
This one over here?
Yeah.
So this, if you were to write it out, is the same as writing, this is a multinomial term, and it's shorthand for 7 divided by 1 factorial, divided by 1 factorial, divided by 0 factorial, that's just 1, 2 factorial, 0 factorial, and 3 factorial. So that term is the same as this. And this is the same way of saying, if you had, how could you order 2 A's, 2 B's, 1, 2, 3, 4, C, D, E, 1, 2, 3, 4, 5, 6, 7. It's saying, how many ways could you order these letters? And you can think of that, A's represent your outcomes of type 1, B's represent your outcomes of type 2, Z's outcome type 3, 4, and 5. So the number of orderings of those letters is an important part of calculating this probability. Just like the orderings in a binomial random variable, you take the number of coin flips and you do n choose k, which is the same as n factorial divided by k factorial times n minus k factorial. So in the binomial you have this term, in the multinomial you have this term, and it's the generalization of that binomial term. And the derivation for why you need it is the same as the reason for why you need that choose term for the binomial. Good question. Yes?
Out the probability of getting this exact roll of dice.
Yeah, isn't that weird? Looking at the probability of the exact roll of dice where I'm talking about how many 1s, how many 2s, how many 3s, how many 4s, how many 5s, and how many 6s. And implicit in your question is such an important question. Why would you do this? And it's not that important for dice. I don't think there's that many games where this is a really critical idea. But it will be critical for figuring out who wrote the Federalist Papers. So we will take this as a metaphor, like the coin flips was a metaphor. How many times in life are you I'm going to flip a coin n times, and I need to know the probability of getting 5 heads? Never. But how many times has the binomial showed up as a metaphor? A ton of times. So the exact same thing's going on here. Okay, let's bump this up a notch. You guys are ready. Just to focus in on one thing. These are all random variables, and this 6th random variable says the number of times that 6 appeared, outcome 6 appeared, was 3. And so that's what that assignment to that random variable means. Okay. And an important thing here is in this equation, this over here would be the probability of getting a 6. In dice, it's 1/6 for all outcomes, but the multinomial allows for the generator of the multinomial to say what's the probability of each outcome, in which case you would put the probability of getting a 6 here if it was something other than 1/6. Okay, and you saw the 6 3 times. Okay, great. We've done this, all right. We did the pedagogical pause already. I'd like to bump this up a notch and actually make it useful. So we're going to give you guys an introduction to natural language processing, but first there's a question.
Going back to the dice example, in the case, do all the probabilities, even if they're given, have to sum up to 1?
Absolutely. If you say, here's the probability of outcome 1, here's the probability of outcome 2, 3, 4, 5, 6, and you're telling me there's only 6 outcomes from a dice roll, if I add up those probabilities, it must be 1, because they must be mutually exclusive, and they must span all outcomes that are possible from one dice roll. Yes?
Just to clarify, the 7 choose thing is different from a regular choose function.
Yeah, it's this. It's the multinomial, which is just writing 7 factorial to 1, 1, 2. This is called the multinomial. Yeah. So it's funny. The whole thing's called a multinomial distribution. That's the multinomial function. Yeah.
I can see the pattern of why the things on the bottom are why what they are, but I can't immediately see like the proof behind it. Like, why am I just putting those numbers there, and why does that work?
Yeah, good question. You know when you did coin flips and we did that very full derivation? It's like we're going to have this many outcomes that have 1, 1, 1, 0, 0, 3s, 2, 4s. And so it's like we're going to have this many rows where you have the particular outcome quantities that we saw. Any one of those rows has this probability, because this is the probability of seeing that 1, 1. It's probably seeing that 1, 2. They might have been in different orders, but multiplication has this property that they're all going to come to the same number, and this is how many rows there are. So if you go back to the coin flipping, it'll be the exact same derivation. Good question. Yes?
I know you said that the binomial coefficient is like a special case of the multinomial, but I don't really understand like the n minus k factorial part and how that comes from the multinomial.
Okay. If you think about the binomial, we've been super cheeky. When you flip n coins, there's 2 random variables. How many heads and how many tails? And if you have n heads, how many tails do you have? Sorry. If you have k heads, how many tails do you have? N minus k. So it's kind of like there's 2 outcomes. There's n experiments, 2 outcomes, types. Some are heads and some are tails. Good question. Yes?
So we're allowed to group, for example, some variables together, 4, 5, and 6. If we don't group separately.
Yeah. You could have one catch-all outcome, which says it's like a bunch of these outcomes I'm going to put together. That would be allowed, as long as you can tell me the probability of that catch-all. Okay. You guys want to take this to the next level and do some natural language processing? Oh, yeah. Okay. So probabilistic text analysis starts with a simple idea of just talking about words that people could write on English. And for the longest time, this was theoretical, but then the internet was invented, and we scanned all the books, and we looked at all the websites, and we could actually figure out probabilities of words. So you could take the entire internet, and you could think about what's the chance that if you chose a random word on the internet, it would be the word the. And we won't get into that exact number, because even though it's large, it's pretty small, there's lots of words. I'll tell you that it's larger than the chance of getting the word Pokemon. You guys buy that? Another fun fact that you can tell your friends, the probability of somebody writing the word Stanford on the internet is greater than the probability of somebody writing the word Cal. So we can talk about the probability of any particular word occurring on the internet. If you take a paragraph of text, or a document more generally, it will have many words in it. Strip out all the punctuation, and you can count how many times each word appears. You can say, how many times did Cal appear? How many times did Pokemon appear? How many times did the appear? You can think of those counts, and if you think about the distribution of those counts, we could model it using the multinomial. And to give you a concrete vision, in our multinomial, we're rolling dice n times. We're still going to be doing that, but now our dice is this massive dice. And on this massive dice, there's an outcome for every word in the English language. And not every outcome is going to be equally likely. So you have this big dice with every word. It's got Pokemon somewhere, it's got Stanford somewhere, it's got Cal somewhere. And when you're writing your document, it's like you roll your dice and it says the. You roll your dice again, it says best. You roll your dice again, it says class. Roll your dice again, you get is. Roll your dice again, CS109. And the claim is, just kidding. The claim is if your document has n words, if you looked at the counts of each words, then we could use a multinomial to model it. It's just like the dice problem, but hopefully more interesting. The one big difference is instead of having 6 outcomes, we have outcomes for every word. And the probability of each outcome is not going to be 1 over 6 or even 1 over m. It will be defined by how likely that word is to show up in an English document. Okay, if people are curious, there are just a bit under 1 million unique words in English. It depends on the internet. Defining a word is a hard thing, but the dictionary says there's about a little bit under 1 million real words. Lol. Okay. So let's give you an example document, and this is a real case that people first use the multinomial for, spam detection. We'll talk a little bit before that. Here's a document. Pay for Viagra with a credit card. Viagra is great, so are credit cards. Risk-free Viagra, click for free. This has 18 words in it. And so if you wanted to think about this as a multinomial, you might say, okay, Viagra showed up twice, free showed up twice, risk showed up one, credit card showed up twice, and 4 showed up twice. Now, you could think about this as a multinomial, and it turns out if you think about the probabilities, you could think about if somebody was writing a spam email, what's the probability that they would write each of these words? And you get a slightly different dice shape than if you took a normal English language. And you could say, what's the probability of seeing this particular multinomial outcome in the world where the writer is a spam author? In that case, we can just use the multinomial formula. There are 18 factorial, or 18 words, so there's 18 factorial up here. And then you do the counts for each words. That gives you your coefficient. Then you would say, okay, what's the chance that a spam writer writes Viagra? Square that, because Viagra shows up twice. What's the chance the spam writer writes free? Square that, because free shows up twice. And that would give you the probability that someone would write this if they were using the spam dice. And you could say also, what's the probability someone would write this if they were just using the English language dice? And hopefully you get 2 numbers. And fun fact, this was the original spam classification, was based off of this. Okay. So in the world where you thought about this particular author's dice, this probability of seeing the document was a multinomial of counts of outcomes. How many times you see this outcome? Outcome, 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 outcome. And we can use the multinomial joint probability to get our chance of seeing this exact document. Okay. Now, we're not going to be doing spam classification today. We're going to be doing something slightly different. We're going to be trying to answer this deep historical question, who wrote the Federalist Papers? Many of you guys might know what the Federalist Papers are, but if you didn't, when the US was just a baby country, they were trying to ratify the Constitution, and there was a series of papers that were written to convince the public to ratify this Constitution, say like, we should have a Constitution. And they were all written under the same pseudonym, Publius. They weren't just one author, it was several authors writing these foundational papers that we now think of as a critical part in the history of this country. But then later on, we found out who was Publius. And does anyone know who Publius was?
James Madison, Alexander Hamilton, and this third guy.
John Jay.
John Jay is the third guy. Yeah, okay, the 3 people wrote all these papers, and this sounds pretty straightforward. And later on their deathbeds, they're like, yeah, it was totally me, and I wrote papers 1 and 7. There was a whole bunch of them. I wrote 136, 100. And generally, that was a fine way to figure out who wrote them, except on their deathbeds, some of them claim to have written the same one. Ooh, drama. So there's 85 essays, as we mentioned. They're all written on the same Publius, but the real authors were these 3 people. And we want to know who wrote each essay, and we're going to use probabilistic analysis of the words in the essays to figure out which of the authors actually wrote it. And I'm going to focus on a particular one, paper 53. Alexander Hamilton and Madison both claim to have written paper 53. Here is Federalist Paper 53. Please don't read it, but there it is. Trust me, that is in fact Federalist Paper 53. And over here, I have all the text from all the Federalist Papers that I know Madison wrote, and here I have all the text from the Federalist Papers that I know Hamilton wrote. And my question for you is, can you tell me who wrote unknown.txt? Interesting. Okay. Where do we start? This is your data. You're going to write a program that's going to answer this question. I've got the data for us. And you have to figure out an approach for this. You have a whole collection of words. There's lots of ways of thinking about probabilistic models of words, but the one that we focused on in CS109 in this class is counts of words within a document. How many times does a particular word show up in a document? These documents would allow you to estimate the probability of these people writing any particular word. And once you have an idea of what's the chance that Hamilton would actually write divisions versus Madison's probably writing divisions, then when you get over here, you can think about how many times did divisions show up here, and which author do I think is more likely based off of their probabilities of writing those words. We're not just going to focus on the one-word divisions. Instead, we want to think about all the words that show up in unknown.txt. So you have all these words. You want to know the probability of authorship. And using the documents that I gave you of Hamilton and Madison, you can know the probability of any word given the author. So this is a fun problem to think about. So I will give you guys just a moment to stare at this and think about what you would do. Don't talk about it with a partner for a second, and then you do talk about it for 2 minutes. So just think for yourself. Okay, talk about it with a friend if you want to. How would you approach this problem? Okay. Oh, how fun. Well, hello again, says Bayes. And why does Bayes show up here? You can think using a multinomial about the probability of seeing a document given a particular author. But what we would really like to solve in this problem is the conditional the other way around. We want to know the probability of an author given a particular document. And Bayes' theorem, which we learned in our core probability, is also going to apply when we get into the world of random variables and probabilistic models. Particularly, what we would really like to know is how likely it is that the probability of Hamilton writing this document given all the words. I'm going to use D for all the words. It's my shorthand form. We don't know this direction, but the multinomial gives us this direction. It says, if I know Hamilton's the author, I can talk about how likely is this collection of words using the multinomial. I have to have a prior belief of Hamilton. I have to have this weird term for the probability of the document. What about prior belief that it's Hamilton? Let's start with that, because that we can argue about. There's two things one could do. You could say, based on my long history of understanding the Federalist Papers, I have this prior belief that it's more likely to be Hamilton. I'll express that as a 0.8. Or you could say, I want to be pretty fair to everybody. So before I go into this analysis, the probability of Hamilton is going to be 0.5. I'm going to say, before I look at any words, my belief that it's Hamilton is equal to my belief that it's Madison. And I'm going to set that to be 1/2. So if you set this to be 1/2, you can think about this as the probability of a collection of words given Hamilton. That will be a multinomial, and we're just left with this awful term at the bottom, which we'll deal with somehow. This awful term at the bottom, though, I'd like to talk about it for a second, because it shows up in Bayes' theorem a lot. So normally if you have, probability of H given D equals probability of D given H times 1/2, because we're going to say the probability that he wrote it before we see any data is 1/2. Normally what you do on the bottom is you find some sort of expansion for probability of D. And what we've often done in the past is probability of D given H times the probability of H plus the probability of D given Madison times the probability it's Madison. And again, we're going to say the probability of H is 1/2 and the probability of Madison is 1/2. That's what we'd normally do, and that's totally fine. That's a good way of getting rid of probability of D. This thing, we call it the normalization constant, and we're often thinking about cool tricks to get it to go away. This is going to be the probability of the document given Hamilton, and we can just use a multinomial. We can say, here is this document. We can look at how many times every word shows up. So this is the joint probability mass function of the multinomial, and it's got this multinomial coefficient, and then it has probability of each word type raised to the power of how many times that word type goes. And we're just going to, instead of multiplying this 6 times, we're going to multiply it over every kind of word that we see in the document. It will just be a straight multinomial. We can put a 1/2 for probability of H, but we still have this problem of probability of D. Can I show you something cute that we can do? Sometimes I just don't like that probability of D. So I can solve this equation for probability of H given D. I could do the same thing for probability of Madison given D. And in both of these equations, I'll end up with a probability of D. And what if I was feeling super cheeky and super cute? I'm like, I don't want that probability of D, but if instead of thinking about the exact probability of Hamilton, if I just looked at the ratio, is the probability of Hamilton greater than Madison? I could know it by dividing these two terms. We've never done this before. But I can take this term, divide by that term, and if it's greater than 1, I know probability of H must be greater than the probability of M given D. So I can calculate this term and then figure out authorship. Does that sound cool? The coolest thing about that is when you write these two things, you're like, adios probability of D, I'm never seeing you again. And the 1/2s cancel out, and you get that this ratio is just going to be equal to these terms. One more beautiful thing comes out. This multinomial coefficient is the same whether or not you're thinking about Madison or Hamilton as the author, because you're looking at the same unknown document, and the same unknown document has the same count of every type of word, and those two coefficients are just going to go away, and this whole problem is just going to reduce to this. A very fundamental, a well-justified approach leaves us with, if you can calculate the ratio of these two terms, you should be able to figure out who wrote this document. How cool is that? To the code. Now, I'm going to give you this calculation. I'm going to calculate for Madison, and I'm going to calculate the multinomial. I'm going to loop over my unknown document, get the probability of every word, see how many times it shows up. So first, this probability will be Hamilton as the author writing word I. Then next time I call this function, it'll be Madison, the author, writing word I. And I'm going to calculate exactly what I had on the slides, and we will know once and for all who wrote this. This is starter.py. Now, if you look at some things I just pull out from the dictionary before I show you any results, I first say, I compute Madison's probability of every word. So the probability that Hamilton writes the word Congress is 0.001. That's very high. I do not write Congress that much. Madison either. Madison's probability of writing the word Congress is 0.00016. Congress shows up once in the document. It's looking a little bit like Hamilton. Anyways, there's 2,172 words in this document. And then I calculate this term and I calculate this term. We'll go over the exact details of this code later, but when I calculate those two terms, I get the probability of the document given Hamilton is 0, and the probability of the document given Madison is also 0. Heartbroken. I'm heartbroken. Does this tell me who wrote it? No. Is it because probability is 0 for everything? No. These should not be 0 probabilities. What has gone wrong? What a mystery. The mystery continues. Come back on Friday and we will figure out what is the true answer to this question of who wrote this document, and think about it in the next couple of days. What has gone wrong here? Don't forget, let us know, when are you taking the finals?